Hello everyone, my name is Samir Verma and today we are discussing concepts of steel structures. So steel structures is one of the important subject in civil engineering. So let's begin with the concepts. So first, steel is an alloy of iron and copper and carbon content is around 0.23%. Fine, so steel is alloy of iron and copper. Next is, what is the use of carbon? So as the carbon content increases, the brittleness, hardness and strength of steel will increase, but ductility will decrease. And ductility we can find by using this formula. Next, stainless steel is an alloy of iron and chromium. So steel was alloy of iron and copper, but stainless steel is alloy of iron and chromium. Next, in point number 5, you can see that here this is Young's modulus of elasticity of steel and Young's modulus of elasticity of rubber. So Young's modulus E represents stiffness property of the material, and you are very well aware of this formula, that change in length is equals to P into L upon AE. So this formula here, when this E decreases, then deformations are more, or vice versa. So if E is more, then del L will be less. It means that a material is stiff. In the next point, aluminium. This is Young's modulus of elasticity of aluminium, and this is Young's modulus of elasticity of steel. And you can see that aluminium is almost 1/3 of the Young's modulus of elasticity of steel. Aluminium is increasingly used for structural purposes because it requires less maintenance and its strength to unit weight ratio is high. So strength to unit weight ratio of aluminium is high. And what is the disadvantage of aluminium? It is that the deformation are high for the given load and it is costlier. So these are some disadvantages of aluminium. Next, we will be discussing standard steel sections. So first, we will be discussing the beam sections. So in beam sections, we have ISLB and ISMB. So what is the use of ISLB? First, how it is notified. See, it is written as ISLB. LB means light beam. 300 is overall depth at the rate 0.41 kilonewton per meter. Kilonewton per meter means weight per unit meter run. So first is ISLB. It is used as roof beams where loads are relatively less and in vehicle chassis. So for relatively less loads, we use ISLB. And ISMB is used for floor beams where loads are relatively more. So it has high moment of inertia and about x-axis with compared to y-axis. So it has more moment of inertia in x-axis rather than y-axis. And it has less lateral buckling strength. Next is ISHB. It is similar to medium beams, but thickness of flanges and web are high. So ISHB. HB here represents heavy beams. Next is ISWB. WB represents wide flange. So they have high moment of inertia about y-axis also when compared to ISMB. So they have high lateral buckling strength, so they can be used as columns. So these have high moment of inertia about y-axis also, right? In ISMB there was a high moment of inertia in y-axis, but in this We have high moment of inertia in y-axis also. So it can be used as columns and has a high lateral buckling strength. High lateral buckling strength. Next is T sections. So there are ISHT and ISST. It is IS wide flanged T section and IS long legged T section. Next we have angles. We are represented by ISA and ISBA. So ISA are equal angles when it is 100 into 100 into 10, and ISA 150 into 100 into 10. Here you can see they both are unequal angles. Here it is 150 and 100. And the another one is bulb angle. So here, what is bulb angle? So bulb angle actually increases the stiffness of the angle. It is used in shipbuilding, so it stiffens the angle more. Next we have channel sections represented by ISSC, that is S is for special and C is for channel. 300 is again the overall depth, and 0.41 kilonewton per meter is weight per unit run. So here you can see 300 is the depth. Next we have flats. ISF, F represents flats. So in flats we will have width and thickness only. Width and thickness. So 50, here it is width, and 8, ISF 8 represents the thickness. Next we have plates represented by ISPL, IS sheets represented by ISSH, IS round bars represented by ISRO, and square bars represented by ISSQ. Now moving further, what are the permissible stresses in steel structure? So we are talking about the permissible stresses for designing the steel structure. First we can discuss the maximum permissible axial compression stress. So axial compression sigma AC is equals to 0.6 Fy. Here AC means axial compression. Second one is maximum permissible axial tensile stress. So here also sigma AT represent axial tensile, and it is 0.6 of Fy. Fy is the yield strength. So it is in tensile members or ties. Next we have maximum permissible bending compression stress, that is sigma BC, which is equals to 0.66 Fy. Next we have maximum permissible bending tensile strength given by sigma BT. It is also 0.66 times Fy. Fifth, we have maximum permissible average shear stress. So average shear stress tau VA. So this is average shear stress. It is 0.4 Fy. And this is the formula for average shear stress. This one. Next we have permissible maximum shear stress. Here I am writing tau VM. M represents maximum, and it is 0.45 times Fy. Fy is the yield stress. The next one is the maximum permissible bending stress. So it is represented by sigma B. It is 0.75 Fy. Now there are some points worth noting. So what is stress? So its stress can be classified into direct stresses and indirect stresses. So direct stresses, we have direct tensile, direct compression, and direct shear. And in indirect stresses we have bending stresses, torsional stresses, shear stresses. So direct tensile or direct compression can be direct stress due to application of load, and it is given by load upon per unit area. Fine. And bending stresses, we have here a stress diagram which is 0 at the neutral axis, and at the top and bottom flange it is stress in compression and stress in tension, right? So sigma BC, actually I have made a mistake here. It should be sigma BC is greater than sigma AC. It should be greater than, because of the non-uniform stress distribution. Next to note is that permissible shear stress is very less because ductile materials like mild steel are very weak in shear. So we have already seen in the previous slide that the shear stress was around 0.4, but the direct compression and axial forces stresses were 0.6. So permissible shear stress is less. Next point to note here is the bearing stress. It is nothing but compressive stress developed at the contact surface of two different materials. So here you can see there are two materials, first this one and this one. So compressive stress will be the direct stress, and bearing stress will be at the surface of the different material, here, somewhere here at the surface. Now next important thing while designing steel structures, factor of safety. So how do we consider the factor of safety? So factor of safety for sigma AC direct it is axial compression, permissible stress in axial compression. So factor of safety is given by yield stress upon working stress, which is Fy, and 0.6 Fy working stress we have seen earlier. So this gives 1.67. So this is factor of safety for axial compression. Next, factor of safety for bending compression. It is Fy upon 0.66 Fy, that is 1.5. So this is for bending compression. And factor of safety for tau Va, that is average shear, it is 2.5. Next we will be discussing the permissible deflections. So maximum permissible horizontal and vertical deflections, here it is given by span upon 325. Span upon 325. So it is given in IS 800 1984. And again, for manually operated cranes, permissible deflection in gantry girders is given by span upon 500. And same way for electrically operated cranes up to 50 tons capacity, the permissible deflection is span upon 750. And if the capacity is more than 50 tons, then the permissible deflection is span upon 1000. So you can see as the capacity is increasing, the permissible deflections are decreasing, and you can find these in IS 800 1984 and IS 800 2007 as well. Now there are some special cases when we have to increase the permissible stresses. So when wind and earthquake loads are considered, permissible stress in steel structures are increased by 1/3% or 33.33%. So we have to increase the permissible stresses when wind and earthquake loads are considered. Next, when wind and earthquake loads are considered, permissible stress in rivets and welds are increased by 25%. So when we consider wind and earthquake loads, permissible stress in rivets and welds are increased by 25%. So rivets and welds we will be discussing in the coming sessions. As of now, I would like to show you some the nomenclature used in the rivets in this joint. So first is the pitch of rivet. So I have shown this pitch by P. So what is pitch? It is the distance between two consecutive rivets measured parallel to the direction of force. So parallel to the direction of force means this is the direction of force. Here it is tensile. See, there are two plates which are kept one upon another, and they have been joined by using the rivets here. Fine. So this is one plate, this is another plate, and these are joined by using rivets. So what is pitch? Here you can see. So what is pitch? This one is pitch. The distance between two consecutive rivets. This is pitch. Next we have gauge distance. So gauge distance is also the distance between two consecutive rivets, but it is measured perpendicular to the direction of force. So this is the direction of force. Perpendicular means this. So here you can see G. This is gauge. I have represented by using G. So this is center to center of the rivet, but in the perpendicular direction of the force. So this is your gauge distance. Okay. So next we have end distance. What is end distance? It is the distance between center of a rivet and the edge of the plate element in direction of the load. Edge distance, it is the distance between center of the rivet and the edge of the plate element perpendicular to the direction of the load. Here also one is in the direction of the load and another one is in the perpendicular direction of the load. So in the diagram you can see end distance. So this will be the end distance from center of rivet to the edge of the plate in the direction of force. And edge distance, this one, it is from center of the rivet to the edge of the plate, but in the perpendicular direction to the load. So that is all for today. Thank you.